Okay, so welcome to Math 310 Modern Algebra. This is lecture 18. And so we're going to do more groups today and then do some applications of some of the stuff we've been talking about, small differences between rational numbers and irrational numbers and what kind of consequences that has. So after we finish this, after we come back from Halloween, we're going to then get into looking at groups in much greater detail. I'm going to try to prove some results about the structure of certain groups. If I tell you it has certain properties, what do we know? What kind of groups are possible? And so we ended the last lecture by talking about trying to find roots of polynomials using good inputs. What do I mean by good inputs? I mean the coefficients of the polynomial and simple operations, adding, subtracting, multiplying, dividing, and then nth roots. And there's a beautiful theorem that says that, while you can write down the explicit solution for polynomials of degree up to 4, and, we saw the nightmare that was the solution. Here it is. This was the cubic, all 3 roots, and this was one of the roots of the quartic. It's not pleasant, but it's explicit. If I change the coefficient of the x term, the linear term, just a little bit, you can actually see how that changes the roots. It's wonderful. Unfortunately, in general, we don't have closed form expressions like that. And so the theorem is that once you have a polynomial of degree 5, a general polynomial of degree 5 implies that you can't write down the roots explicitly in terms of what we discussed. And so for a specific example, you can use x to the 5th minus x minus 1. That's a great example of something. Now, how do you prove this? This is beyond an introductory course. This is what you would see in the sequel class. And this uses a subject called Galois theory, and it deals with groups associated to roots of polynomials. So given that this is a class on groups, it makes sense to talk a little bit about what comes next. What would you see if you continue in mathematics? And so a little bit of notation. So we have G as a group, and H is a subgroup of G. We denote the left cosets of G by G/H. And so we've seen examples of this before. So for example, we could let G be Z, and maybe H could be 12 times Z. And then when we looked at, Z mod 12Z, that would be the set of cosets. So we could write that as, 0 plus H, 1 plus H, all the way to 11 plus H. And we can talk about, how would you, add and subtract cosets? Do you have inverses to cosets? And so the hope is that maybe G/H is a group. And then to understand G, 1, understand H, 2, understand G/H, and then 3, understand putting together. So this is a major theme in mathematics. Break into simpler pieces. So the natural question is going to be, which subgroups H are good choices for something like this, where we can break things down, and G mod H is going to be a group. So that's something that you could try to explore right now, is you could take some groups, you could take some subgroups, look at the set of cosets and see, do you get a group from this? And so a good way to try to define multiplication is, let's say we have 2 cosets, C1 and C2. Each one is going to have some representative element, say G1 and G2. And then we'll define the product of those 2 cosets. We'll have the coset G1, G2H be the product G1, G2. So let's look at a specific example. So we have Z mod 12Z. So let's take coset maybe 3 plus 12Z and maybe 8 plus 12Z. So we need an element in each one of these. Can somebody give me an element in 3 plus 12z?
Eight.
I'm sorry?
8.
Okay, that would be in the second one. And something in the first one, 3 plus 12z.
3.
3. And I'll put another one we could have done is we could have done 20 and we could have done 15. And so now let's look at 3 times 8, 12z. That would be 24 times 12z.
Attention.
Which
determined.
coset do you think that is?
We check on your black sports watch. Please turn to identifying claim. Again, attention determined. This came through TSA security checkpoint. Leaving behind your black sports watch. Please turn to identifying claim.
So what do you think this would be?
It should be the same as 12z, right?
So is this 12z? So 12z is equal to ... minus 24 minus 12, 0, 12, 24, ... And so if we want 3 times 8, 3 plus 12z times 8 plus 12z to be a coset, the only one it could possibly be is 0 plus 12z. But if we have the 24 here, it's going to be a bit too large. So what we could do is we could say what we mean by 24 12z is the unique coset containing 24. So it's the coset containing the product G1, G2. So one of the things we showed earlier is, recall, 2 cosets are the same or disjoint. So if I give you an element, it's in one and only one coset. So this gives us a nice way to define multiplication. It will be the unique coset that contains it.
Return back to the allegiance.
So it's worth looking at, some of the different groups we could study. So there's a lot of very famous groups. One of the most famous is the dihedral group. And it's defined as, it has 6 elements. E is the identity. R1 and R2 are 2 rotations. F1, F2, and F3 are flips. So the rotation here, R1, it sends 1 to 2, 2 to 3, 3 to 1. It's rotating counterclockwise. R2 is rotating clockwise. 1 goes to 3, 3 goes to 2, 2 goes to 1. Similarly, if I look at the flips, F1 is flipping about the line. So 2 goes to 3, 3 goes to 2. For F2, we flip 1 goes to 2, 2 goes to 3. So if you think about it, everything should be expressible using one of these. Each one of these is different from all the others, right? If you look at it, none of them are going to send the numbers 1, 2, 3 to the same new set of numbers 1, 2, 3. How many ways should you be able to reorder the numbers 1, 2, 3?
Factorial.
Say that again.
3 factorial.
Good. 1, 2, 3 is 3 factorial, which is 6. So these are the 6 different ways. And you can start trying to figure out, are things commutative? Does flipping 1 followed by rotation 1, does that equal first rotating 1 and then flipping 1? And we can do the calculations, we can write things down. So F1 is going to be, we have 1, 2, 3. 1 goes to 1, 2 goes to 3, and 3 goes to 2. And then R1 is 1, 2, 3. 1 goes to 2, 2 goes to 3, 3 goes to 1. And we can compute the other order. 1, 2, 3, 1, 3, 2. 1, 2, 3, 2, 3, 1. And so if we compute this, 1 goes to 1, 1 goes to 2, so we get 1 goes to 2. On this side, 1 goes to 2, 2 goes to 3. I don't have to finish it out. This is already enough to know that they're not the same. I'll finish it out anyway. 2 goes to 3, 3 goes to 1. And then just to make sure everything is right, 3 goes to 2, 2 goes to 3. On the other side, 2 goes to 3, 3 goes to 2, 3 goes to 1, 1 goes to 1. And so we see that they are different. So there's a lot of geometry here. So we're talking about how can we flip these different elements. And in Galois theory, which is trying to study which polynomials can be solved with roots, radicals, sums, products, all that stuff, it turns out you define a group that acts on the roots of the polynomial and which flips, which interchanges are permissible. Okay, so we talked a little bit about cosets before. We want it so that it doesn't matter which representative you use. So if I take a coset, let's say G1 8, let's say G1 G2 H versus G1 prime G2 prime H. We want these to be the same. And so if G1 and G2 are in the same coset, I'm sorry, if G1 and G1 prime are in the same coset, what does that mean for G1 and G1 prime to both be in C1? It means G1 is equal to maybe say A1 plus something in H. G1 prime would be A1 plus H1 prime in H. So their difference is going to be something in H. So I'll leave it as an exercise for you to go through and do the algebra to show that you will end up in the same coset, that you're going to basically just be shifted by something in H, so it's not going to make a difference. Okay, let G be a group, H is a subgroup, and then takes any element G and G. The G conjugate is all things of the form G inverse HG as H ranges over little h. If the group is abelian, what is this? If G is abelian, then what is G inverse HG equal?
H.
It just equals H. So in some sense, this measures how far you are from being abelian. So it's possible that you could still be equal to H without being abelian. So we say H is a normal subgroup if G inverse HG equals H. So it's not the same as being abelian, but it's at least something. It's a little bit of a weakening. And so, the standard example is if G is abelian, then you clearly will be normal because G inverse HG is always going to be G. But there are times when you can have G inverse HG equals H with the group not being abelian. So again, explore. I'm not giving you that much homework. What I would suggest you do is try a couple of groups. Get your hands dirty. Try to do these calculations. See if you can find a normal subgroup. So you can, try looking at lots of different things. If you looked at, Z mod 12Z, you might have a lot of things to play with. Do you expect to find normal subgroups here? Do you expect the subgroups to be normal here? What do you think? Is this group abelian or not?
Yes.
Yeah, so if it's abelian, should things be normal here? Yes. Right? We're not expecting to see anything interesting here. Now, a few moments ago, we actually looked at a dihedral group, and we showed that this group is not abelian. So this would be a really good place to try to look for normal subgroups. Can somebody give me some subgroups of this? There's two subgroups you should be able to give me immediately.
Rotations and slips.
Well, I want the two easiest subgroups first, then you can say your answer.
Itself.
Itself, so D3, and what else?
Just the identity.
Just the identity. So those should definitely be normal. And now you said the rotations. So what would be, we could do E1, R1 squared. What's R1 cubed going to be? What would happen if we rotate 3 times? We rotate once, we get to 2, twice we get to 3, 3 times we come all the way back to 1. So R1 has order 3. So that would be a normal subgroup. I'm sorry, that would be a subgroup. Similarly, we could have E R2 squared. What about another subgroup?
EF1.
Good. So we would have EF1, EF2, EF3. And then the question is, are there any other subgroups? Are these normal? So I'll let you explore and gather some data. Okay, so, standard proposition, if we have a homomorphism of groups, then the kernel is a normal subgroup. So what does it mean? Phi is a homomorphism means what? It means phi of G1, G2 is phi G1, phi G2. And we know phi of the identity goes to the identity. So the kernel of phi is the set of all G in G such that phi of G goes to the identity. So we want to show that this is a normal subgroup. So we showed earlier that it was a subgroup. So showed earlier is a subgroup. So let's consider G kernel of phi, where did they put the G inverse on the left? Okay. G inverse kernel phi G. Does this equal kernel of phi? So what do you think? Well, consider any x in G inverse kernel of phi G. There has to exist a y in the kernel of phi such that x equals G inverse y G. Because what does it mean to choose an element in G inverse kernel phi G? It means I have to have some element in here, and I multiply it on the left by G inverse and on the right by G. So we want to show that this is in the kernel of phi. So let's look at phi of G inverse YG. This equals phi of G inverse phi of Y, phi of G. Technically, we only did phi of a product is the product of the phis when you have two elements, but if you had more than two elements, it's not a big deal. You would just prove it by induction. So by induction, phi of G1 through Gn is phi of G1, phi of Gn. What do we know about phi of Y? So what's true about phi of Y?
It goes to E.
It equals, say it again,
E prime, sorry.
E prime, exactly. It equals E prime. Therefore, this is just phi of G inverse E prime phi of G, which is just phi of G inverse phi of G. And now what can I do to phi of G inverse phi of G? I'm trying to show that G inverse YG is in the kernel of phi. I'm trying to show that it gets sent to the identity. I need to compute what this quantity is. What do we know about phi of G inverse phi of G? What does that equal?
E prime.
But how did you get that? What's the next step?
Phi of G inverse times G.
Phi of G inverse times G, and that's phi of E, which is E prime, and that finishes the proof. So this now motivates a bit why we were looking at conjugation by multiplying on the left by G inverse and on the right by G. If things are abelian, the G inverse and the G hit each other and they cancel. We see now that when we're looking at the kernel is a normal subgroup. So this is one way to prove that something is normal, is we can go back to the example we had, and if we can show that any of these subgroups down here, for instance, if we can find a map phi where this is the kernel, or we can find a map phi where this is the kernel, then we would know that those are normal. So frequently there's more than one way to do something. The easiest way might be to do the calculation directly, but that might be a long, tedious calculation. If we can happen to find a nice map, a group homomorphism, which has one of these as the kernel, then we're done. So the question is, can you find such a map? So this now gives you two different ways to think about this problem. Okay, so the next is just, continuing some properties of groups and subgroups. So G will be a group, H will be a subgroup. We will always try to use G for group and H for subgroup. So if G inverse HG is contained in H for every G, then H is normal. So it's enough to just check one way. And this is for every G. If everything is finite, this shouldn't be too bad because they have to have the same number of elements. But we could have infinite groups. So why is it enough to do G inverse HG is contained in H for all G? this is a really nice trick. Instead of G, take G inverse. And now we know that this is supposed to hold for all elements in the group G. Let's take it for the element G inverse. So now we get G inverse H, G inverse is contained in H. But what is G inverse inverse?
G.
It's G. We get G, H, G inverse is contained in H. Or H is contained in G inverse H, G by multiplying on the left by G inverse and the right by G. And so we actually get we get the other inclusion. So if you can do this for all elements, take G the first time, take G inverse the second time. So this cuts your work down in half. So that's A. For B, for all G and G, the conjugate set G inverse HG is a subgroup. Right, so let's just go through carefully and show that all the properties hold. And then the last is for all G, the map that sends the subgroup H to G inverse HG, the mapping from H to the set G inverse HG, defined by H goes to G inverse little hg, is a group isomorphism. So if H is finite, then H and its conjugates all have the same number of elements. So again, this is just unwind the definitions. So I'm going to leave B and C for you to look at. If you have trouble proving those, let me know, and we can do the proof in class on Tuesday. So try to do these. So try to prove. And if you want to send your proofs for me to check, to just see how you're doing, absolutely, feel free to send. Okay. Let G be a group. H is a normal subgroup. Suppose that if we have G1, G1 prime, G2, G2 prime all in G, imagine G1 prime H equals G1H and G2 prime H equals G2H, then G1 prime, G2 prime H equals G1, G2H. This is basically saying what you would expect to have happened. Notice it's saying that we have a normal subgroup. So if H is a group, is H equal to H? What do you think?
Yes.
Oh, yes. Why?
Wait.
So you are correct.
I was thinking of the midterm problem, but the midterm problem, it was commutative, so yeah.
Right. What's a good element in H? What's one element we know has to be in H?
E.
Yeah. So as E is in H, E times everything in H is clearly contained in H times H. So we get H is contained in HH. By closure, H1, H2 in H implies H1, H2 is in H. Therefore, HH is contained in H. So the answer is yes. So again, it's the proof technique. We choose a special element. The only special element we know is E. That gives us one inclusion. That gives us the inclusion H is contained in HH. And then for the other one, it's coming from closure. Okay, so why is this useful? Well, if G1 prime H equals G1 H, that means G1 prime times E has to equal G1 H1 for some H1 in H, right? Because the cosets are the same, there has to be some element, for any element in one, it's got to match up with an element in the other. So if I look at G1 prime hitting E, that's got to live somewhere in G1H. I don't know where, so I'll call it H1. So we now know that G1 prime times E equals G1H1. So that means G1 prime is equal to G1H1. So we get G1 prime equals G1H1 and G2 prime equals G2H2 for some H1, H2 in H. So if I look at G1 prime, G2 prime, H, this is going to be G1H1, G2H2 times H. Now, we've said that we have a normal subgroup. So because we have a normal subgroup, we can actually say something about H1, G2, H2. So we'd love to move this H1 to the right of G2. And then we would have the two G's together, and then we'd have a product of H's, and then that would just give us everything. And then that would just be some rewriting of the subgroup H. Why do you think we can move the H1 to the right of G2? So the hope is H1 G2 equals G2 H1 tilde. Why do you think we should be able to move it over? What property of H do you think we're using?
Commutative?
I'm sorry?
Commutative?
We don't know H is commutative. What do we know about H? So what do we know? What's our assumption about H? So you've got the statement of the lemma right here. What are we assuming about H?
Normal subgroup.
That it's normal subgroup. So somehow the fact that it's a normal subgroup has to help us here. So let's go back to the definition of a normal subgroup. So normal subgroup says G inverse HG equals H. So what does this mean? So if G inverse HG equals H, then given any X in H, G inverse XG equals some new element X tilde in H. Or XG is going to be G tilde X. I'm sorry, G inverse. I'm sorry, GX tilde. So what this is saying is if I have G, some element G, and I multiply on the left by X, that's the same as multiplying G on the right by some other element X tilde, where X and X tilde live in H. So we can't say, it's not saying XG equals GH. It says XG equals GX tilde. X and X tilde are both in H. So if I take any element G and I multiply on the left by something in H, it's the same as multiplying by something else in H on the right. Not necessarily the same thing, but something related. And so now over here, since it's normal, oops, so since it's normal, H1 G2 would be G2 H1 tilde, some new element in H. And thus we get G1 prime, G2 prime H is the same as G1, G2, H1 tilde, H2, H. But what is H1 tilde H2 times H? If I multiply a subgroup, I'm going to just, by an element in it, I just get back that subgroup. And so this is going to just be G1, G2H. So as an exercise, prove if H is a subgroup and little h is in H, then little h equals H. Basically, more generally, H could be a group. Because we have closure, little h times H, capital H, is still going to just be something in capital H. We never leave the subgroup with this multiplication. So what we're really asking you to prove is that if you have a group and you multiply a group by an element, you still just get every element of the group. And it's very important that we have inverses here, and that's why this works. So again, this is something you should be able to write up rigorously. If you are concerned about being able to write things up rigorously, this would be a great exam problem. Make sure you can do it. Show it to me. If you want me to prove this in class on Tuesday, I will. So my goal is to give you a bunch of things to think about, and then you can choose which things you want me to cover in detail on Tuesday. And so just send me an email so I know which things to be doing. Okay. So what this is telling us is that, if I take two different representatives of the same coset, when I multiply, I really do get the same thing. All right. And so now there's a lot of additional stuff you can do with group homomorphisms and whatnot. And can you define maps on cosets if you have maps defined on groups? And so we'll talk a little bit more about this later. I don't want to go into too much new group theory material right now. I want to give you some time to digest it as we go through chapter 6. But this is what we're doing along the lines of break into simpler pieces. Understand H, understand G, mod H, and then understand how to put them together. That's where we use the group homomorphisms. Okay, so for the rest of the class, and we're not going to go all the way to 11:10 today, probably. I will be hopefully giving a talk about this later in the. Okay. I will hopefully be giving a 50-minute lecture on Benford's law later in the semester, or maybe in the spring at Siena. And so we've been talking about finding roots of polynomials. And we saw that if we have a polynomial of degree 1, 2, 3, or 4, we can write down in closed form the solution, but in general, I've been telling you without proof that you can't do it for degree 5 and higher. And you might say, who cares? Yeah. So here's a couple of numbers. Yeah, the last one is the square root of 3. First one is pi. The next one over here, has anybody seen this number before? The second one.
Or if not,
Yeah, this is Learyville's constant. And it's defined as the sum of 10 to the negative n factorial. So you keep going further and further and further before you add the next 0. And so because 0 factorial and 1 factorial are both 1, that's why we got the 2 over there. This looks almost rational. You know, if I were to break the number over here, I've got a huge number of zeros before I get the next one. My error is extremely small, but it's not a rational number. It is an irrational number. And so the question is, do small differences like this really matter? Do they really make a difference? Can we just approximate things? And if we can, over what time scales can we approximate? So out of curiosity, how many of you saw the great totality from a few years ago, from April 8th, 2024?
Yeah, I saw it.
Was Siena in the line of totality?
No, we needed to drive up, but
Yeah,
like,
you got to drive a little bit.
yeah.
We had to drive about 3 hours to Middlebury to see it. And you know, my daughter was unfortunately still very sick back then. So we drove up a little bit the night before. There were so many people driving, it actually took more time to check into the hotel than it took to drive to the hotel. And we heard some people say they didn't want to deal with the traffic. They weren't going to do the last hour of driving, the last 90 minutes of driving. They didn't think it was worth it. They thought, oh, seeing 96% of the eclipse is enough. And so I tried to take some, pictures. The ones on the right are by myself. The other ones are better ones from the web, where you can just really see the difference. And 96% is not the same as 100%. 99% is not the same. It's just amazing as it suddenly comes into play. One of the things I try to get under all of my students' radar is to glean information from maps. We had some maps early in the semester. This is one of the favorite maps I've seen. It's Airbnb occupancy. The more orange it is, the closer it is to 100% on April 7th. Does anybody notice anything interesting?
the big line of red, I assume that's where it was 100%.
Yeah, this is the line of totality. And you can see the reservations, impacting that. And so again, general advice, whenever you are given data, try to look and see which part should you focus on. Where's the interesting stuff happening? The other thing is adopt to changing times. So this is on the right was a restaurant, a yogurt place in Middlebury. They were normally closed on Mondays. The owners were extremely smart and realized, hey, maybe given that it's totality, we should actually be open today because maybe a lot of people are going to be coming through. So they did a booming business. We actually hit them twice because after totality was done, neither my daughter nor I wanted to sit in line with everybody leaving. So we said, let's get some more. We'll wait, and then we'll go afterwards. So just general advice for life, be aware of opportunities, take advantage of opportunities. Along those lines, if any of you are applying or want to apply to graduate school and want a letter of recommendation, I'm happy to give you some extra problems to do or do some of the problems I'm suggesting. That gives me more information to be able to write a stronger letter of recommendation. So here is a really natural question. If I consider a lot of sequences of data, I could ask, what percent of the first digits are 1, what percent of the first digits are 2, and so on and so on and so on. And you might initially guess that maybe 10% of the time you're 1, 10% of the time you're 2, all numbers are equally likely. And then you realize, well, you're never going to start with a 0 because we write numbers in scientific notation. So 0.001701 would be 1.701 times 10 to the negative 3. So you might change your guess from 10% to 11%. Do you think all data sets will have first digits equally likely? What do you think? If you give me a data set that you don't think is going to have all digits equally likely. Somebody give me a data set. How about temperature? Do you think if you look at the daily high in Siena in October, that all first digits are going to be equally likely?
No.
No. I don't think you're going to see many 8s or 9s. Hopefully you won't be seeing too many 1s or 2s. So you would expect the data to be clustered. If you look at batting averages, if you're not able to bat at least 200, you're really not going to stay in the major leagues. Nobody has batted 400 or higher since Ted Williams in the 1940s. So again, sometimes the data is going to be clustered. And so you wouldn't expect all digits to be equally likely. Amazingly, for a lot of data sets, the probability that you get a 1 is about 30%, and it decreases down to about 4.6% for getting a 9. And this is called Benford's law. And it's amazing how many different places it arises. And because a lot of data follows these rules, you can actually use this to detect fraud in many cases. You have to know if the data should follow Benford's law. And a lot of times people use this in situations where it's not known that the data should follow. So here are some very diverse phenomena. So the first, myself and one of your professors who I know several of you have had for complex analysis, we both study Fibonacci numbers. Fibonacci numbers are one of the best examples of this digit bias. It's almost perfect. The next one on the right is Twitter users by number of followers. Most common iPhone passcodes, I don't want to know how they got that data. Distances of stars from Earth. So in a lot of these data sets, you're seeing this predominance of low digits. Now you have to be very careful. A math test indicating fraud is not proof of fraud. So here's one of my favorite Dilberts. As somebody who has had a lot of their expenses subjected to scrutiny, Dilberts is denied because all of his meal costs are round numbers. He's declared to be a liar or worse. And his response is, I decide what to order based on what totals to a round number after 15% tip. That's worse. But there was an alternative explanation. It wasn't just fraud. So a lot of these tests can be used to suggest something might be going on. It's not a proof, but it's a suggestion. It's something you should look at. It's something that's worth investigating further. And then you need more refined techniques, but it tells you how to allocate finite resources. So there's a lot of applications of this bias. So one is analyzing round-off errors in computations. Another is determining optimal ways to store data. Another, and I've done some work and happy to talk about this outside of class, is detecting text and image fraud. Some people have used it to try to detect fraud in election results. I'm happy to talk about some of the successes and failures of these methods. So a little bit of background material so you get a sense of what is needed. So a lot of the key concepts to do this important mathematics are things we've been doing this semester. And this is one of the reasons why I wanted to talk about this. Whenever you teach a class, at the end, you should be able to answer the who cares question. Why did you take this class? What did you get out of this? Sometimes it's, I learned how to attack problems. Hopefully the content is also useful. So the first thing we need is modular arithmetic. You know, A equals B mod C if A minus B is an integer times C. The next big input is just writing things in scientific notation. If I give you a positive number x, I can write x as some number between 1 and 10 times 10 to an integer. And so that's scientific notation. So for example, 2020.1701 in scientific notation would be 2.02011701 times 10 to the third. So two numbers, A and B, have the same leading digits if and only if their significance are the same. Well, that makes sense because the other part is just adding how many zeros we have. So it's a nice exercise to show this equivalence. Now, if I take the log base 10 of A, if I write it in scientific notation, it's the log base 10 of its significand plus the log base 10 of 10 to the k. Well, the log of 10 to the k base 10 is just k, it's just an integer. And that's why two numbers, A and B, will have the same leading digits if and only if they have the same significance, because they will then differ by some integer power of 10. And when we take the logarithms, it gives us an integer. So hopefully you've seen the function e to the ix is cosine x plus I sine x. This is a very famous Euler identity. And sometimes instead of x, we use 2 pi. And so typically, you can't just chop off the integer part of a number and feed it into a function and get the same result. But if I'm looking at sines and cosines, I only care about the argument up to an integer multiple of 2 pi. And so if I want to study e to the 2 pi I u, it's enough to study e to the 2 pi I u mod 1. So in this situation, if I look at things in terms of exponentials, I only need to understand my input up to an integer. And that's bringing us back to what we were doing earlier, the clock arithmetic and writing things in the significand. So the stuff we've been doing has tremendous applications. This leads to the subject called Fourier analysis.
Attention all passengers, if you just came through security checkpoint and you were missing your black over bag, please
So
return to-
we need a couple of concepts from analysis or probability. So the first is the notion of equidistribution.
No longer have your black-
So we say a sequence yn is equidistributed mod 1. Sometimes you'll say uniformly distributed, sometimes you'll say evenly distributed. If the fraction of the time mod 1 it lands in an interval AB is just B minus A. So remember, we're looking at it mod 1, so AB lives inside 0, 1. So AB is a subset of 0, 1. And so if I give you an interval of length 1/2, then we would expect if the sequence is equidistributed, half the time it should land in the interval. If I give you a sequence of length 1/3, then it would be about 1/3 of the time. So there's a beautiful theorem that if I give you any irrational number beta, then n beta is equidistributed mod 1. It's a nice exercise to show that if beta is rational, then it's not equidistributed. It's going to be cyclic. If I give you beta equals 1/5, then the set of n beta mod 1 would be 0, 1/5, 2/5, 3/5, 4/5. What comes after 4/5? What's 5/5 mod 1?
0.
0. What's 6/5 mod 1?
1/5.
1/5. So it would just cycle. So if I give you a rational number, it's going to just keep cycling. The amazing thing is if I give you an irrational number, it's going to be equidistributed. So because I had to prepare things ahead of time, I chose the square root of pi. And so I want to see how often is the square root of pi, is n square root of pi mod 1 in various subintervals. So I chose intervals of length 1/10. And I looked at the first 10 points. Does this look like it's falling evenly? Yes or no? Or do you want more data?
From
Need
this
more
data,
data?
Yeah, I want more data. It doesn't look terrible. 8 out of the 10 times, we expect it to land 1 out of 10 times, and it is landing 1/10 for most of them. And then once it doesn't make it at all, and once it makes it twice. I chose my number so that it wasn't perfect. If I look at it 100 times, it's pretty close. If I look at it 1,000 times, it's very close. If I look at it 10,000 times, you can see very slight fluctuations. It seems to be converging very quickly. And this leads to the natural question, how quickly do things converge? And the rate of convergence is going to be a function of how irrational the number is. So this is a bit too much to get into in one lecture right now, but for those of you who are interested, I'm happy to chat more about this. How irrational the number is impacts how quickly it converges. So let's try to see what's going to give us this digit bias. Why are we going to see 1 about 30% of the time? So I write my number in scientific notation. So I write it as a significand, which is a number between 1 and 10, and I write it as 10 to an integer power. Okay? So if I look at this, the top is my significance. And the bottom is going to be the log of the significand. Well, the log of 1 goes to 0, and the log of 10 goes to 1. So if I want my number to have a first digit of 1, it has to live between 1 and 2. But the log of 1 is 0, the log of 2 is the log of 2 base 10. So this distance here is the log of 2 base 10, which is about 0.3. Similarly, over here, if I want it to be between 9 and 10, this is going to be the log base 10 of 10 minus the log base 10 of 9. And just, writing it out a little bit more carefully, if I give you some digit d, and I want to know what's the probability I have a first digit of 6. So if d equals 6, d plus 1 would be 7. And so I have to look at what's going on over here. And so d plus 1 goes to the log base 10 of d plus 1. D goes to the log base 10 of d. And I look at their difference. And then we use the log. The difference of the logs is the log of the ratio. So that's the same as the log of d plus 1 over d, or the log base 10 of 1 plus 1 over d. As an exercise, if I look at the log of 1 plus 1 over 1 times the log of, plus the log of 2 plus 1 over 2, plus the log of 3 plus 1 over 3, plus plus the log of 9 plus 1 over 9. Those are all the probabilities. What should the sum of the probabilities equal?
1.
1. And by using the log laws, this is the same as the log base 10 of 2 over 1 times 3 over 2 times 4 over 3 times 10 over 9, which is the same as the log base 10 of 10, which is 1. So this is a nice consistency check that we are assigning probabilities. The probability sum to 1. And we have basically a nice mapping from one space to another. We've been talking about group homomorphism. Sometimes it's easier to look at one thing than another. So the digit bias to the Benford's law, the digit bias, it's really coming from being equidistributed under the log base 10. So if I give you your data set, then you take the log base 10 and you throw away the integer part, then in many data sets, that's evenly distributed, uniformly distributed, equidistributed, however you want to say it. If we don't take this logarithm and chop off the integer, if we just look at the numbers, we get the digit bias. The bias is really just because of how we're looking at things. If we do this nice transformation, we now have something that's uniformly distributed. That's much more natural. Not many of you have done statistics, but if you have, and you've done regression, the method of least squares, we frequently use a log transform so that we can get a linear relation. So, as I've said before with Rubik's Cubes, it all comes down to what's the right way to look at things? What's the right perspective? If you find the right perspective, the problem often becomes easy. So to prove the Fibonacci numbers are Benford, the Fibonacci numbers satisfy beautiful recurrence. Each one is the sum of the previous two. And there's a closed form expression for the nth Fibonacci numbers. It's called Benet's formula. And the way you get to Benet's formula is actually there's several ways. One way is you make this educated guess. I'm going to guess that the nth Fibonacci number is just r to the n. This is not an unreasonable guess. And the reason it's not unreasonable is we know Fn is going to be less than or equal to twice Fn plus, Fn minus, let me rewrite. We know Fn plus 1 is going to be less than or equal to Fn plus Fn, or Fn plus 1 is less than or equal to 2 Fn. So Fn is growing slower than 2 to the n. Similarly, can show grows faster than the square root of 2 to the n. So we know root 2 to the n less than or equal to Fn less than or equal to 2 to the n. It's not unreasonable to guess from this that maybe it's growing at the rate of r to the n. At the end of the day, if I prove something, it doesn't matter how I got there. So the method of divine inspiration is telling me, hey, try r to the n. And if I plug in r to the n into the relationship after doing some algebra, you get that the roots for r that work are 1 plus or minus root 5 over 2. 1 plus root 5 over 2, that's the famous golden mean. And then as a nice exercise, show if r1 to the n satisfies the recurrence relation, I can multiply by c1 and it still satisfies. And similarly, if r2 to the n satisfies the recurrence relation, I can multiply by c2 and it still satisfies. And because the relationship is linear, I can add 2 of these and there'll still be a solution. The other thing you could do is you could say, screw all of that. I'm going to just guess that this works, and I'm going to just plug this in and show by doing some algebra that it works. All of those are fine. As n gets very, very large, can somebody tell me what this goes to as n goes to infinity?
Infinity?
Why do you think 1 minus root 5 over 2 goes to infinity?
Wait, is that sum gonna be?
I'm not asking about the sum. I'm just asking 1 minus root 5 over 2. What does this piece over here go to as n goes to infinity?
Well, hold on, is that greater than 1 or less than?
Well, let's think. Root 5, that's more than 2 and it's less than 3, right?
Right.
If it was equal to 3, 1 minus 3 over 2 would be negative 1. So this is greater than negative 1 and it's less than 0. So this number is less than 1 in absolute value. So this goes to 0.
Okay.
So it basically tells you the nth Fibonacci number is essentially just this beginning part over here. And so the log base 10 of the nth Fibonacci number is basically the log base 10 of 1 over root 5, which is fixed, plus n times the log base 10 of 1 plus root 5 over 2. All we have to do is show that that bracketed quantity is irrational, and now we can use the result from before. That if you take an irrational number, n beta is equidistributed mod 1, and once that's equidistributed, if that's the logarithm of your sequence, then your original sequence is Benford. So a data set is Benford if its logarithms mod 1 are equidistributed. So that's what we showed over here. If we can show the log base 10 of 1 plus root 5 over 2 is irrational, then we know that the logarithm of the Fibonacci numbers are evenly distributed, therefore the Fibonacci numbers are Benford. So it's a nice homework problem. Show the log base 10 of 1 plus root 5 over 2 is irrational. So it turns out most recurrence relations will be Benford. And so what I want to do is I want to end with 2 to the n. So 2 to the n is growing pretty rapidly. So the numbers are getting larger and larger and larger. I'm only going to display the first 30. And then on the right, I'm going to look and see what fraction of the first 60 have a leading digit of 1, have a leading digit of 2, and so on and so on. So here are the observed probabilities. Here are the Benford probabilities. Do you think it looks Benford? Roughly.
Yeah, rough.
Roughly. I mean, it's not looking uniformly distributed. It's not looking like all digits are equally likely. Which point do you think is the least, is the worst? Which fit do you think is the worst? Which fit do you think is the best?
First is the best fit,
Yeah.
and ninth is the
Yeah, and then the last is the worst. And one of the reasons the last is the worst is the Benford probability for getting a 9 is the smallest of all the probabilities. This is the rarest event. One different value would have a huge impact. So the question is, do we expect the values of 2 to the n to be Benford? Do we expect them to have this bias? If you look at the data on the left, you should notice a pattern. 6, 4, 6, 5, 5, 3, 6, 6, 7, 1, 0, 8, 8, 6, 4. It takes a while before we get a new leading digit in that sequence. It almost looks periodic. It almost looks like we get the same value again. So 2 to the 10 is almost 10 cubed. What is 2 to the 10 equal?
1024.
1024. And in fact, in computer science, there's 1024 megabytes in 1 gigabyte. Even if you analyze mega and giga, you would think there should be 1,000 megabytes in 1 gigabyte. It's not 1,000, it's 1024 because computers love powers of 2. If 2 to the 10 equaled 1,000, then every time I increase by 10, I would just get the same number with 3 zeros padded. And I wouldn't get Benford's law. I would just keep getting the same values again and again and again. Notice in the first 30, we have no 7s, we have no 9s. It takes a while before we finally see one of them. Okay? So I chose 3 numbers. Everybody I think knows E and pi. The other one is the Euler-Mascheroni number, which you might have seen when you're looking at the harmonic sum. How many people say yay or stats if you've taken a stats class? I'm not hearing many voices. The 21st century is going to be the century of data. You need to learn how to analyze data. I cannot force you to take a stats class before you graduate. I strongly urge you to take a stats class before you graduate. If you know stats, if you know probability, if you can code, you will almost surely be able to get a job. You may not like your job, but you will have a job. It is extremely important to analyze. So in probability, there's something called a chi-squared test. To compare observed with predicted. We don't need to know that much about it other than the test exists. And if the observed is given by the predicted, theory, then for data like ours where you have 9 digits, 95% of the time you should get a value of 15.5 or less. So does it look like gamma is following Benford's law? Are we getting values of at most 15.5? I would say yes. Do you agree? It looks pretty good.
Yeah.
And so what we're doing is we're looking at the first digits of, looking at first n digits of n gamma and e and pi for 1 less than equal to little n less than equal to big N. Okay. What if instead of looking at gamma, what if we looked at e? Does that look Benford? What do you think? Benford? Are those values pretty small? Are they less than 15.5?
Yes.
Yeah, they look pretty small. What about pi? What do you think?
No.
Well, it started off large, then it got smaller, but then it got large again, got small, but it never got as high as 15.5 again. What would you like to make a better answer? What should we do? What should we do so you can make a better answer?
Gather more data.
Gather more data, right? One of the things you need to learn out of this class is gather more data. So I'm going to plot what's going on. And I'm not going to just do those special values. I'm going to do all the values from 1 to 1,000. Now, unfortunately, if you look at these numbers, 46.65 is the largest value. 0.03 is the smallest. That's a lot of orders of magnitude. That's 3 orders of magnitude between them. If I try to put that on the same scale, they'd be dwarfed. So what I'm going to do is I'm going to plot the log of the chi-squared values, because that way it's going to be compactified a little bit. So if you look at the blue, these are the chi-squared values for E. Those look pretty good, much less than the log of 15.5, which is 2.74. What about the values for chi-squared coming from pi? Do you notice anything interesting?
It looks periodic.
It looks periodic. Perfectly periodic?
Not perfect.
So the amplitude is decreasing. Maybe almost periodic with amplitude decreasing. So this is the. Can you estimate what the period is? Anybody want to try to guess the period?
Maybe 175-ish?
Okay, maybe 175-ish. Okay. If I was a magician, I would say, no, you've never seen me before in your life. First time in the class, right? Can anybody tell me what pi equals approximately?
3.1415.
Excellent. What does pi squared equal approximately? You stopped at pi? You didn't memorize higher powers? Well, if you had done a few higher powers, you would eventually come to pi to the 175. And pi to the 175 is approximately 1.0028 times 10 to the 87. So what this tells you is every time we increase n by 175, it's almost as if we've added 87 zeros. Not quite. It differs by this really small amount, the fact of 1.0028. But that is enough to give us Benford's law. It takes longer for things to converge. It takes longer for that to arise, but it's going to happen. And this is one of the things I really want you to get out of today's lecture. That small differences can eventually matter tremendously. It's almost 10 to the 87. It was almost 10 cubed. That small little difference makes a huge impact long term. Okay, and then just a couple of takeaways. If you want to hear more about stuff like this, I'm always happy to chat. Also, I've posted some more extensive slides and some talks I've given on this. If anybody's interested in applications of Benford's law, I'm going to stop recording right now and happy to chat about some of those.